So record and then start share screen. Let's see. Okay, I need to get to the right place. Yeah. So yesterday we started the example. Okay. So yesterday we discussed clustering. Yesterday we discussed clustering regarding this example. And if you recall, so this unit is regarding clustering. Okay, and is clustering supervised or unsupervised learning?
Unsupervised learning.
It's unsupervised.
Yeah, unsupervised learning. Okay. So it's unsupervised. Keep this in mind. Okay. And the three approaches that we discussed, the first is k-means. The second one is hierarchical. Is it? And the one we discussed is we call agglomerative clustering, is it? And the last one is dense-based DBA noise. I don't remember the exact name. Okay, but I remember it's dense-based. Okay, let's take
density-based spatial cluster.
Yeah, spatial cluster. Okay, so the name here is a little bit of wrong. Okay, so anyway, we learned the three approaches. Okay, and we started discussing about this example. Is it? And the data set we just manufacture our own data, is it? So we have three cluster data, is it? So clearly we can see, is it? And then we already discussed the k-means, is it? And if you recall, the k-means, the disadvantage of it is you need to preset, is it, the number of clusters. But that's a disadvantage because with a lot of samples, if you cannot visualize, it's very hard, especially if there are a lot of features. Is it? It's not like over here, it's two-dimensional. You can kind of scatter plotting, is it? Then it's easy to see. But if there are a lot of features, then it's going to be very hard, is it, to visually see the cluster. Is it? So it's hard to find the optimal number of clusters, is it? So yesterday we also discussed some approaches to help find the optimal number of clusters. Is it? One is called elbow. You remember the elbow is the distortion, is it? The distortion, or we call it inertial. Is it the initial relationship with the number of clusters? Is it? And graphically, you remember it's like an elbow, is it? So this turning point, this elbow point, is it, will tell you the best number of clusters, is it? So here is the number of clusters in GLOW. Here is the inertial, is the distortion. The distortion is the sum of the square of error, is it, in cluster. In clusters, so that's elbow, okay? And the second approach to help determine the best number of clusters is, we call it silhouette. Okay, yeah, silhouette, the word, let's find it. Silhouette. Yeah. You remember about this silhouette. The silhouette basically is bar plotting, is it? But it needed to use the silhouette. The silhouette coefficient, is it? And as he learns the matrix, they have the silhouette. We can find the silhouette values, is it? And for silhouette, then it give you the relationship. It's kind of like the bar plotting, is it? It's some kind of like, you remember, if you have all of your, this should, is it? All of your cluster, is it? If they are the same width and similar, not the same, similar, okay, and similar length, is it? Then it is, so then if your cluster over here, it's each cluster, is it? Each individual cluster, is it? And if the data distribution within the cluster, is it? If the silhouette looks something like this, is it? Then it's the good choice of clusters, is it? Cluster. And if you have something like, if you have one cluster like this, the other cluster is like this, definitely that's, if you only have two clusters, that's not a good cluster, okay? So with k-means, we can use use this to help us to find the best number of clusters. Is a silhouette. So if you have some silhouette bar drawing like this, that's good, is it? Otherwise, if you have this kind, that's not a good choice of clusters, okay, number of clusters. And for the hierarchical clustering, is if hierarchical clustering, we use the dendrogram. So let's take a look what that is. So here, similar, we are going to manufacture our own data set, okay? So it's a pretty simple one. You have 3 features, okay? So these are features, okay? Anyway, we call them X, Y, Z, okay? And over here, you have samples. Samples. Over here, it's quite simple. We just use 5 samples, okay, to see. Okay, so this is data frame, etc. And then let's see, okay. And if you recall, for the hierarchical clustering, it's from your original data set. You need to come up with that, we call it proximate matrix. Is it? And the proximate is the row is regarding each sample. Is it? And the column is also about the sample, is it? And you need to find the distance. The distance. And do you remember yesterday we discussed the distance? There are a number of ways you can measure the distance. Do you still remember we have single linkage? Is it? And we have complete linkage. And we can also use like average linkage. Is it? And we can also use centroid, is it? So there are a number of ways. And who still remember, if you use a single linkage, generally speaking, the clustering looks like what? it can lead to the clustering. And for complete one, so the visual difference between these two, the clustering is what? Who still remember? For the single linkage, okay, so the question is, so how about let's put a multiple choice here. So we have long chain shape clustering, is that we can also have sphere, more sphere type of clustering, is it? So between these two, single linkage easy to lead to what kind of clustering?
Be a long chain.
Yeah, very good, very good. You can put the answer to the chat, okay? So long chain, is it? And the complete linkage lead to more sphere, is it? The sphere type, okay? So, and over here, so when you come up with the proxy matrix, is it? So the cell, the entrance in this matrix is that distance, is a distance, is it? And the distance calculation based on your choice. Okay, what kind of choice you want to use? You want to use single linkage, or you want to use complete, or you want to use average? Is it? We also have a WOD, is it? And we also have a general, a very general formula. You remember, general formula, and that apply to all of the cases, but each one has their own coefficient, something, is it? Something like that. Then you can make it to either single linkage or complete, is it? Or average, is it? So something like that, is it? So the general one. Okay, so that's the review regarding the hierarchical clustering, is it? So it's based on what we call proximate matrix, is it? Okay, so the entrance for the proximate matrix is some kind of distance, is it, between two sample points, is it? And the way to find it, the first round, you find the smallest, is it? So if we take a look, like in this case, the smallest is between 1 and 2, is it? Then you remember, so here is 1, sample 2, sample 3, sample 4, sample 5, is it? So the first will be this two, is it? Here you have the distance, is it? So you can cluster these two together, is it? And then we can keep doing, is it? And after you cluster these two, you remember the proximate matrix will be changed, is it? So you want to have 1, 2, is it? So you will group these two together, is it? ID 1, 2. Is it 1, 2? Is it? And then you recalculate the distance, is it? Between samples and to this cluster, is it? Then you may find, oh, this 2 is the smallest, is it? And then next you may find this 2 is small. And then last you only have a single cluster, is it? Then you are done, is it? And totally how many cluster you want to have, then you can set up some cutoff distance, is it? And you cross cut, and you will see in this case, oh, that means 2 clusters is going to be good. Okay, that's called hierarchical clustering, okay? Okay, then let's see. So for this, we come up with this raw distance calculation, is it? Based on the datagram, is it? And then over here, if you take a look, is it? And this is not from sklearn, okay? This is from sign sine pi. Is it psi pi? Is it psi pi? And it has a hierarchy, and you import the linkage. Okay, and for this linkage, then you can specify what kind of distance. Is it, of course, we use Euclidean distance, is it? But you want to use single linkage or complete or average or what, is it? So you need to specify the distance calculation, is it? Specify. Okay, so we then come up with the distance we can based on what you specify here, is it? And then next, let's see. Okay, so anyway, so this is similar, is it? You say, okay, I'm going to use complete, is it? And Euclidean, okay, linkage, is it? And over here it says second approach is you use condensed distance matrix, is it? And the third one is you can also input simple sample matrix, is it? So you use the original values, is it? We can also do that. Okay, so then how do we draw a dendrogram? Is it, if you want to draw a dendrogram, it's not from pyplot, okay? You need to import a dendrogram from SciPy, okay? Cluster and hierarchy, is it? Then you have this dendrogram, okay, dendrogram. And with dendrogram, then you specify that matrix, is it? And you also specify labels, is it? And over here, then we can see, is it? And of course, if you draw, you still need to use the pyplot, okay? But just remember, it's the dendrogram itself is not from pyplot. And then here we have this dendrogram, is it dendrogram? Okay, so you have all of the samples, is it? So dendrogram, the x-axis is all samples, okay, and this y is the distance. So whatever you pick, is it, for the calculation, is it? And then you can clearly see, is it, oh, the first time it does the clustering 1 and 2, 0 and 4, and then you cluster. So this is a cluster, is it? And then you group, you merge. We merge, is it? That's how hierarchical clustering work, is it? Hierarchical clustering, it starts with what? Each sample is a cluster. Okay, you consider each sample is a cluster, is it? Then later on, you use distance to merge, is it? Find the closest. Is it based on whatever is the distance definition? Is it? Then you merge, is it? So that's why over here I merge. After I merge, so I have these 2 data points merged in one cluster, is it? And then you find, okay, the next one is close. Then I merge these 3 together, is it? And this 2 is a cluster, is it? And then you say, okay, finally I merge everybody together as a single cluster, is it? But that's not the goal, is it? The goal is you find the optimal number of clusters, is it? Optimal depends on where you cut off, is it? So if you pick up your cutoff line, cutoff distance as 7, then you will have 2 clusters, is it? 2 clusters. But if you choose 5 cutoff distance, is it? Then you can have 3 clusters. Is this? Oh, so it depends on where the cutoff distance. Okay, so this is the idea about clustering. Okay, and let's just skip this. Okay, and over here, so that's about the visual drawing of the dendrogram. Okay, and in sklearn, we can do so the way we just discussed, bottom up clustering, hierarchical clustering, is it? This is called agglomerative clustering. Okay, in sklearn you can use. And how do we do that? You can just directly have agglomerative clustering, and you specify the number of clusters, is it? And you specify what kind of distance you want to use, is it? And the way to merge, this is regarding how to merge, is how you merge. Okay, I'm going to use the complete linkage to merge, is it? So then you have clustering, is it? And then you can predict, is it? Because over here we have 3 clusters, is it? So this is the first sample. First sample, is it? From its cluster number, then we know it is the second cluster, is it? And here is the second sample. Second sample, is it? And from its cluster number, we know that this is the first cluster. First cluster, is it? And here is a third cluster. So you can then clearly find the cluster labels for each sample. Okay, for each sample. So this is the clustering, is it? And over here it also shows you can also choose just 2 cluster, is it? And similar. So you can specify the number of cluster, okay? Okay, the last one, what we discuss is, this is dense space. Dense space. Dense space, is it spatial clustering? Okay, I don't remember what the other 2 letters represent. Okay, but anyway, this is based on density, is it? So density based. Oh, I'm sorry, it's not dense, it's density based. Okay. So what does the density base mean? Is it? So in density base, it has core points. It also has border points and noise points. And there are 2 parameters you need to think about. Is it radius? So the sphere's radius, is it? So basically it's some distance you define, is it? And the minimum number of points, is it? So that's the idea, is you define some radius, is it? Some radius with the radius, some sphere with the radius epsilon, is it? Then if you have a sample, so this is a sample, is it? And you use this sample as a center and you can get a sphere. And then you will check if this sphere has the minimum number. So suppose minimum number is 5. If it has 5 data points included, okay, in this case, I do have, is it? Then this point is defined as core point. Core points. Core points, is it? And for this one, okay, suppose within the distance, is it? Within the circle. Then if you count, it doesn't have, it only has 3 points, is it? So it cannot find 5 points within that space, is it? Space. then that's why we call it a border points, is it? And if a point is here and it doesn't, if you draw a circle, it doesn't have any other data point, then that's considered as noise points. Okay, so this is the concept of density based. Okay. Okay, with density based here similar is that we generate, so we manufacture the sample data. Is that sample data is moon-like. So we have this sample points, sample points. And then we are going to try with different cluster algorithm. Is that the first one we apply is k-means, and we're just going to pick 2 cluster. Okay, 2 cluster. Then we are going to do prediction, and we are going to do some drawing. Okay, the k-means. The second approach we do is agglomerative clustering. Same thing, we do 2 cluster. Okay, we use complete linkage. Okay, and then after this, we can take a look. Is it the result of this? Is it? So the first is k-means. Is it? For k-means, you can see this is the result of a k-means clustering. So it group the left side points together and the right side points together. Is it like this? So that's its grouping, okay, cluster. So it define this 2 cluster. And with agglomerative, is it? It's kind of similar. Is it? This 2 cluster, okay. And then let's see. So looks like this 2 doesn't have huge difference, is it? But you can also clearly see, is it? This 2 clustering, it's off from its original clustering. Is it? It's off, is it? But you can go home to try. Maybe you pick different linkage, it will change, is it? So you can try that, okay? And then let's see, if we use dense-based, okay, so dense-based, then you need to specify the radius, is it? The minimum sample points, is it? And of course, you also need to specify the distance, is it? A calculation, okay? And then in this case, what you can see, yeah, so if you use dense-based, so in this case, the dense-based DB scan, this DB scan. So dense-based clustering, then it can catch its original clustering feature, is it? So this example just shows us, is it, if your sample distribute differently, then you should try with different clustering, is it? So also remember, clustering is unsupervised learning, okay? Okay, that's this example. And then let's take a look at a second example, okay, regarding clustering. The second example is about some product categories that in grocery store, that so we have so over here we have some sales data, okay, sales data, and the data generally it has some channel region. If it's fresh, it's milk, grocery, frozen, detergent, is it? So some other kind of products, is it? Okay, and over here we can try with clustering, is it? Over here to give us some data discrete. So total sample we have 440, is it? Okay, and over here, in this example, the first thing we do is we also do normalize. And why we do this is because over here, we do need to do this is because you need to calculate the distance. Is it you want to bring all of the data to the same scale? Same scale, is it? And data pre-processing in this regarding, we do normalize. Is it? Who remember there is another way to do data pre-processing to bring data to the same scale? What is the other one? Who remember?
Is it a standard scaler?
Yeah, very good. You can send your answer to chat. Yeah, standardization, is it? Is it? That's regarding mean and the standard deviation. Is it normal, just speaking, minimum and maximum? Is it? So anyway, we can do normalized data. Is it? So then we have, you can see the data is normalized. Is it? Okay, data is normalized, and what over here we first try to do is we are going to do the hierarchical clustering, is it? And we are going to do the dendrogram, is it a dendrogram? And here you can also, you see, with the dendrogram, is it the hierarchical, this hierarchy model, is it? You can also call it linkage, is it? And the linkage this time, you use the normalized data. And the method is we pick the word linkage. Okay, so remember this is a word linkage. We have single linkage. We have complete linkage. This is what? This is a little bit of more complicated, is it? Okay, so anyway, to choose this word linkage, is it? And it gives us a data. And with this data, you can see, is it? It's very messy, is it? At the bottom. Why? Because there are 440 data points. Is it? You cannot see anything, basically. It's all crumpled together, is it? Okay, so let's see, how do we solve this issue? Is it if you do want to visually see it? Is it? And here just show you pick some cutoff distance. Is it? If you pick 6 cutoff distance, then you will only have 2 clusters. Is it? Okay, so if I do want to clearly see, is it, how the cluster, where I can see, is it? And if you take a look over here, is it? So here it didn't start from the bottom. It started somewhere, the hierarchy, is it? Dendrogram somewhere, is it already clustered? So those are already clustered. Is it? Okay, then how do we get this kind of dendrogram? Is it? So over here, we still use the scale data, the linkage as word, is it? So you can pick the truncate mode. Okay, truncate mode. And here the mode says the last P. Okay, last P says show only the last P number of merged clusters. Okay, not from the original one. Okay, and what is a P number? You can also determine. Here says I'm going to show from 24 merged clusters. Okay, and because we wanted to draw it and label it clearly, is it? You can also specify the rotation font size. Is it something like that? And also, if you want to get some distribution impression in truncated impression, is it? We can also do that. So anyway, so this shows then you can truncate your original dendrogram. is it? Then in this case, it kind of give you some clear sense, is it? Clear sense. Okay, so that's about this dendrogram, is it? And we also learned in sklearn you can choose the agglomerative clustering, is it? So in this case, okay, we say, okay, we want to just choose 2 clusters, is it? And the linkage you can choose what? And the distance you can choose Euclidean, is it? And what are all of those values? This tells you each sample's cluster. So it's belong to which cluster, is it? Then you can clearly find which a cluster each of the sample belongs, is it? And then a lot of time, you may also be interested, because in this case, our original data, is it? We have a lot of features, is it? So more than 2 features. When you have more than 2 features, it's hard. It's hard to do scatter plotting to find some pattern. Is it because a lot of time, if you do some scatter plotting with your data set, that may help to see some trends or some pattern of your data, is it? But if there are more than 2 features, it's hard, is it? And previously we learned, is it? If you recall, we can kind of review, okay? So let's see. And so when you have a number of features, and if you wanted to decrease the feature, what's the we discuss is called, we call dimensionality reduction, is it? And who still remember, we learned a number of approaches, very important concept, okay? Who remembers those methods that we discussed? The P, you remember? P represent what? Something, the 3 word. Who remember? Regarding
PCA analysis.
Yeah, very good. PCA, is it principal component analysis? You can send your answer to the chat, okay? So that I can give you bonus point. PCA, is it?
And
Yeah.
LDA.
Yeah, LDA, very good. Okay, LDA. And some other one.
Kernel PCA.
Feature, we can use what? Feature importance. Is that you remember? You remember feature importance with random forest decision tree, you remember? It can tell you, you can, in sklearn, you can collect a feature importance feed, that number, is it? And the other one, you remember, who remembers what this 2 means? L1 and L2 used for what? Who still remember? When we say L1 and L2. Another very important concept in machine learning. Generally speaking, it's also regarding, we call it a hyperparameter tuning. Parameter tuning, is it? And the hyperparameter tuning, generally speaking, is to deal with what? the very two important thing is bias and what is the other one?
Variance.
Variance. Very good. Okay. And variance. Is it? And related with this two, we said generally the model is we solve the issue for what? What kind of issue when we do machine learning model training? There are two kinds of issues, and we try to balance these two. You remember, bias and variance, you balance both. Then you can get the best fitting. Is it? So
Testing
versus
and training.
versus best fitting is what kind of fitting? It's under fitting, is it? And over fitting. So if you recall, high bias lead to what? Lead to underfitting or overfitting? Who remembers? High bias.
Underfitting.
Yeah, it lead to what? Underfitting.
Underfitting.
Yeah. Yeah, you can send your answer to the chat. Okay. It leads to underfitting. Is it? Higher bias means a lot of times what? Your model is too simple. Is it? Your model is too simple. You didn't catch enough features. Is it? Or you don't have enough samples. Is it? And the high variance normally lead to what? High variance.
Overfitting.
Yeah, it's overfitting. Okay, keep all of this in mind. Okay, high variance means what? Your data distribution, is it? It's spread out too much. Is it? Spread out too much. Is it? And spread out too much. That's why the PCA is used to what? To catch the principal component. What is the principal component? Principal component is what? So if I draw the data, so suppose the data distributed like this, is it? So it's spread out along where? Along this direction. Is it? This direction is it's most spread out, is it? So this is the principal component. So this, we call it a principal component. So if you can transform your data distributed along this new component and the orthogonal one of this, is it? Then you can minimize the variance. Is it? Minimize the variance. That's the goal. Is it? So that's PCA. Is it? PCA is, and the LDA is for feature selection, the feature extraction. It's for feature extraction. And then how about L2 and L1? Who remember? We need to know this, okay? Because this is if you in the future work in machine learning, you will see this a lot. Okay, when you do model train, it's not just you know the model that. What is that?
Logistic and linear regression.
No, it's generally speaking, L1 and L2 is for what? For regularization. Is it? Regularization is what? Is to penalize weight. Is it? Penalize weights. And with the model like a logistic regression, SVM, is it? And perceptron, is it? Our goal is to optimize the weight, is it? So that's why sometimes to avoid overfitting, is it? You need to penalize the weight. So that's L1 and L2, is it? L1 related what? With lambda, sigma, wi square. It's weight, square of weight, and you sum them. So this coefficient lambda, is it? In our sklearn, it's the inverse of C, the inverse of C. So that's our goal, to try to regularize this, is it? And for L1, it's lambda, sigma, it's not a square. It's the absolute value of the weight. You sum them together, is it? And you try to adjust this parameter, is it? And this L2 is penalized weight. And for L1, a lot of time it can lead to weight be 0, is it? So then you can also because if weight to 0, so you can filter that feature, filter out the feature, is it? The respective feature, is it? So use L1, sometimes you can also do feature selection. Okay, keep this also in mind, okay. There is also in machine learning a topic, it's regarding feature, we call it feature engineering, okay. Feature engineering, okay, very, also a lot of techniques discussed over there, okay. So feature selection, feature extraction, PCA belongs to feature extraction, okay? And if weight is too small or 0, and you then just filter that fit out, we call feature selection. That's a feature selection. So besides that special feature importance attribute that you can collect from sklearn, is it sklearn? We can also use L1 to do feature selection. Okay, so this is regarding select feature, is it? And here it says with k-means. Okay, it says use k-means. We can get a matrix of cluster, and we can also get feature weights. Okay, and once you have feature weights, then you can also find the feature who have more weight. Okay, and if the weight number is larger, is it? That means it can make a major contribution to the cluster. Is it major contribute to the cluster? Is it? So with k-means, then we can also try to collect these attributes and find the important feature that contribute to the clustering. Is it? So let's see. Over here it says, okay, with that data, is it original, that grocery data? So we have milk, detergent, fresh produce, and something else, is it? And I said, okay, I'm going to just do 2 clustering, Is it two clustering? Okay, with two clustering, if you collect this attribute, dick. Okay, with this, is it? And because I only have two clusters, so this is cluster 1, and this is cluster 2. Is it? And the original grocery data, they have 8 features. 8 features. Is it? And over here, then you can see. We can see all of the feature value distribution. Is it? Then you just find the largest 2. Largest 2, is it? And over here, it says, okay, milk and grocery, is it? So after you collect this 2 most important feature, is it? Then you can do scatter plotting, is it? And with scatter plotting, you can easily see here, is it, the clustering, is it? So here it shows more, is it? But on the other hand, if you, in this case, if we use DB scan, okay, then you will see DB scan won't work well for this data set, for the clustering, is it? So generally speaking, so this example, this part just shows we can also collect the data, is it, from k-means, and then find the important feature, and then you can do scatter plotting, okay? That also help you then later on do some other learning training, is it? Okay, I'm kind of over time today.